Hello. Today we're going to be talking about Chapter 8, Position Tolerancing Fundamentals. Okay, so your objectives for this chapter are, number one, complete feature control frames for position tolerances, properly using the diameter symbol, material condition modifiers, and datum feature references. Okay, to do this, we're going to have to know a little bit about all of those things. Which we're going to be discussing in detail. Number two, sketch the proper location and shape for position tolerance zones. Number three, describe the effect of MMC, LMC, or RFS applicability on a position tolerance. Number four, provide examples that prove the validity of the MMC concept as it applies to position tolerances. Number five, differentiate between fixed fasteners and floating fastener conditions. And number six, calculate the allowable positional, bonus tolerance for a produced part on which a position tolerance is specified at MMC. Number seven, use calculation techniques to verify whether a produced hole locations meet the specified drawing tolerances. Number eight, cite the advantages of a position tolerance when compared to just the plain old coordinate hole location tolerances. And then we're going to talk about the following terms: position tolerance, datum features, basic dimensions, positional tolerance zone, feature control frame, datum reference frame, RFS, MMC, LMC, floated fastener conditions versus the fixed fastener condition, positional tolerance versus coordinate tolerance, and projected tolerance zones. So let's get started here. What is a positional tolerance? A positional tolerance specifies the required accuracy location of features of size and bounded features. It may be used on single or multiple items. Tolerance zone shapes determined by functional requirements of the feature. Typically for a hole, you'll have a diametrical type tolerance zone. Material condition modifiers can be applied to tolerances. Here we got a MMC applied to this tolerance. Here we got an LMC condition applied to this tolerance. Material boundary modifiers can be applied to position tolerance datum references. We don't have any shown in here, but these datum references can go with boundary modifiers if the design requires it. Okay, so the position tolerance. It specifies the allowable variation of location relative to basic positions. So all the positions of the holes are going to be defined using basic dimensions, and then the tolerances of the location of those holes is going to be based on the feature control frame that has the positional tolerance requirements. We're going to talk a little bit about the surface method that takes precedence over the MMC and the LMC tolerances. We're going to talk about two different methods for understanding these tolerances. One is the surface method, and the other one is the axis method. What we need to know right now is that the axis method is only used for RFS, and that the surface method is probably the most applicable to most of what we do. But really, the surface method acts like an MMC type feature control frame. Okay, let's talk about position in models and drawings. Okay, so here's what we have here is some orthographic views. We have some orthographic views of this part, and we have two holes that are located on datum D of this part. Okay, so we have a feature control frame here to establish the positional tolerance of the holes on that part. Okay, so we start with the 2x diametral 37312. That is our size dimension and size tolerance for the holes. There's two of them, and then the feature control frame for the position tolerance is applied right below the size dimension. Therefore, we know that this position tolerance applies to that hole. And here we have basic dimensions that define the locations of the positions of these holes. Okay, so if we look at our datum reference frame in this example, the primary datum here is datum D. And datum D is the surface that the holes penetrate. That is that's the perfect choice for a primary datum, in that that is the plane at which you want to orient this part so you can put those holes in. And then datum A right here is the location in this direction, and then datum B establishes the location all the way back to this surface right here. Okay, so the basic dimensions define the perfect location of the holes, and the feature control frame defines the allowable location deviation. Okay, so this is 5 thousandths at maximum material condition. So in this example, the location applies at MMC. That's what we're seeing right here. Okay, so what does a feature control frame look like for a position tolerance? Here are some examples. We have the symbol, the geometric characteristic for position. This one has a diametrical tolerance zone shape. The tolerance is 18 thousandths, and it has the M and the F modifiers, and it has the 3 datum references. This one here talks about a statistical tolerance analysis, kind of beyond the scope of this book, and then here's some other examples here, and this would be a metric example. Now in some cases we can have combined feature control frames. So in this case we have 2 feature control frames for the same holes, and it's 2 single segments, and that's actually 2 feature control frames. In this case here we have a composite or single feature control frame. We'll talk about this a little bit in the next chapter, a little bit later in this chapter too, how to use a composite and a 2 single segment feature control frames. Now how do we apply material condition modifiers? Okay, so the material condition modifiers may be applied to the tolerance. That's what we're showing here. And the material boundary modifiers may be applied to datum references. That's what we're showing here. Okay, and then rule number 2 requires that all tolerances are applicable at RFS, and all datum feature references are applicable at the regardless material boundary unless otherwise specified. What that means is if we don't have a modifier here, RFS is the condition that is assumed. That's rule 2. And a little refresher here. Rule 1 says that perfect form is required at MMC. So essentially what happens with rule 1 is you have a perfect form boundary that's defined by your maximum material condition based on the limit of size. So in which case the size and the size tolerance controls the form at MMC. So rule number 1 is the perfect form boundary. Rule number 2 is the unless otherwise specified, all tolerances apply at the RFS condition unless otherwise specified. So unless there's a modifier in here, the RFS applies. And again, modifier selection, it depends on the design application, what you need the part to do, how you need to control the part. So these aren't just arbitrary, well, I think I'll use MMC modifier here in this case. No, it has to be dictated by the function of the part and what you expect out of it. Let's talk a little bit about the positional tolerance zone. The feature control frame value defines the position tolerance zone, the size for the axis method. And again, we're talking about the axis method. I'm going to make a separate movie about the axis method versus the it's not pertinent to what we're talking about right now, but I'll make a separate movie for that and post it in this unit. The axis method, it actually came up in chapter 5, and I'll go back and try to explain that to you a little bit better. Okay, so the diameter symbol before the tolerance indicates the shape. Okay, so in some cases we have a circular tolerance zone. In other cases, if we don't have the diametric symbol, we're talking about a total width rather than a diametrical tolerance zone. And then the functional requirements of the feature determine the specified shape. So typically on a hole, your position tolerance zone will be round. With features like slots, we will generally use 2 feature control frames and make it bidirectional. Okay, so what I'm going to do is I'm going to pick up this slide here on the next movie. Thank you.